The first talk will be Recoverable, Fetch&Add, and is given by Hagit Attiya.
So thank you for having me in this not so simple constellation. I'm really sorry none of us could be there. I'm definitely sorry not to be in Strasbourg and not to meet many people there. So this is our paper, Recoverable and Detectable Fetch&Add, and it's joint work with Liad Nahum, Ohad Ben-Baruch, and Hendler, all from Ben-Gurion University. Liad specifically, who should have been giving this talk, is now in an army course, but I see her in the audience. Okay. So in recent years, we've seen a new layer in the memory hierarchy, which is the persistent non-volatile memory layer. And this layer basically combines the persistency and long-term endurance of SSDs and hard drives with the cost and speed that we associate with cache and main memory. And indeed, several hardware companies like Intel and ARM are offering basically processors that include persistent non-volatile memory as part of their configuration. Now, once we have persistent memory, it gives us hope and a desire to create applications that basically continuously operate even when they crash. So processes may crash, but recover, resume operation. And when they resume operation, they find their previous state in the non-volatile memory, and they can continue to operate, so hopefully seamlessly. And one particular way to achieve this behavior in concurrent applications is to take the application, and wherever we have an invocation, whenever we call upon a primitive operation, we will replace this invocation with a call to the recoverable version of the same primitive. And if we have self-implementations of primitive of a recoverable primitive from its non-recoverable version, and perhaps using as well reads and writes, this allows us to have a clean transition of applications to the persistent domain. And for example, if we take this very famous concurrent application, this is the MCS lock, and basically we go over the program, and wherever we have a primitive, we substitute it, we replace it with its recoverable version. So for example, if we have a compare and swap, we replace it with a recoverable compare and swap. And the formal condition we need we use for recoverable, the recoverable primitive is a concept we call nesting safe linearizability, which we defined in a POTSI 218 paper. And the original definition assumed that processes fail and recover individually. In most of my talk today, I will assume what's called as system-wide crashes. So the whole system fails together, and more importantly, it recovers together. And for the rest of the talk, I will also ignore issues that have to do with volatility of the cache. So I will assume that the caches are also volatile, and basically whenever I write something to the shared memory, it goes directly to the shared memory and is persisted immediately. In real systems, we need to introduce additional special hardware instructions like flushes and fences. Now, nesting self-linearizability, which I will define in the next slide, implies a property called detectability, which is basically a famous condition for persistent memory called durable linearizability, and the additional property that when a process recovers, it knows whether its last operation took effect and what was its response. So to define nesting safe linearizability, I need a slightly more formal model of what happens. And basically, I assume that executions include the traditional invocation and response steps. So we call a primitive, an operation on some object, and we get a response from that object for this object. And we also introduce additional crash and recovery steps. And we require histories to be recoverable, well-formed. And basically, we project the history on a particular process, and we require that, first of all, invocations of regular operations match and alternate. So we have invocations followed by matching responses. And then we also require that each crash is followed by a recovery step, unless this is the last step in the execution of this process. And we say that the history is nesting safe linearizable, and in short, NRL, if once we take out all the crash recover steps, the history is linearizable. It's a very nice and elegant definition. And once we have it, we ensure this detectability property. Okay, so that's a definition. But can we implement various primitives using this operation types using this definition? And indeed, in the original paper, we introduced self-implementations of read, write, and compare and swap. And actually, compare and swap also have and has another implementation provided by Ben-David, Ben-Baruch, Friedman, and Way. So a self-implementation, if I didn't say it before, is basically an implementation of the primitive, the recoverable primitive from the non-recoverable version, together with reads and writes. So what we have is basically self-implementations of the very weak operations read and write, and a universal compare and swap operation, which allows us to solve consensus for any number of processes. And it's intriguing and interesting to implement other primitive operations. The compare and swap operation specifically was used in transparent transformation, in particular the capsules transformation, which basically takes a program and partitions it into capsules, each of which includes a single compare and swap, and then transparently and seamlessly translated to be recoverable. So again, we want to have a larger arsenal of primitives, and in particular, what I call the intermediate primitives. And perhaps an interesting one is the Fetch&Add primitives. So Fetch&Add, if you don't know, basically operates on a shared variable, and each operation has as an argument a contribution, basically what I want to add to the variable. The variable contains a counter, and each Fetch&Add operation adds this argument to the variable, and then returns the previous value of this counter. And Fetch&Add is indeed an intermediate primitive in the sense that it has consensus number 2. It allows to solve consensus between two processes, but not more. Like 3 processes cannot solve consensus using Fetch&Add, even if we have as many read-write registers as we want. Okay, and because it has consensus number 2, and because it's general, like being a little bit somewhat strong but not strong enough, Fetch&Add, implementing detectable and recoverable Fetch&Add is more complicated. So to explain why this is complicated, I want to show you an example. So it's a 3-process example, and we'll have each of them execute a single Fetch&Add operation. So the first process executes Fetch&Add with contribution 1, its argument is 1. And it does some work, and then it does not return yet. And then a second process does Fetch&Add with argument 2, and it returns 1. So this means that this Fetch&Add returns the previous value of the counter. The counter starts with 0, so it means that this Fetch&Add depends or has seen the Fetch&Add of 1. And then another 4th process starts Fetch&Add with 3, and maybe does something, maybe not, but again, does not return. Finally, we have another operation doing Fetch&Add and not returning. And then we have Fetch&Add by a 5th process. And this process does Fetch&Add with argument 5 and returns 10, which means that it should be linearized after all these previous Fetch&Adds. So 10 is the sum of all the Fetch&Add operations that I have here. And now in this situation, so in particular, the Fetch&Add must be linearized and must depend on the Fetch&Add of 4 and the Fetch&Add of 3, as well as these two. And at this situation, the crash happens. And when the system resumes, we need to be able to tell what has happened in this execution. Now, for these two operations, we have no problem. They have returned their responses, and it could be recorded somewhere. These three operations, on the other hand, did not return, and we need to figure out what happened to them. Okay, and we have here a hint that they should be effective because they have taken effect, and somebody has returned a value for the counter that depends on them happening. Now, ideally, if we could record everything exactly precisely that happened in the execution, we probably could be able to recover what has happened, but that's too much information, and it's not so simple to record this information using only a primitive fetch and add that is not recoverable itself. Okay. So instead of preserving the whole execution, what we do is actually preserve using a basic primitive fetch and add variable operations. We preserve only vector timestamps for these operations. And as I'll show you later, these allow us to reconstruct what happened in the execution. So here's what we do in the algorithm. And the algorithm follows what I think is a traditional recovery thing. It's actually what they say we should do in talks. We should say we say what we're going to talk to say, then we should say it, and then we should say what we have said. And that's what we do in this algorithm as well. So we record what we are going to do. We do the operation, and then we record the answer that we have. So these are these three basic steps that we have in the operation. And to do that, we have these two memory areas. So one memory area is a very big shared variable, okay, an array that has entries for each process. And this big shared variable is going to be modified by non-recoverable fetch and add. And for each process in its entry, we will keep the sequence number of its last fetch and add operation. Fetch and add in capital, meaning the recoverable operation, the high-level operation. Manipulating this vector is not easy. With the basic fetch and add is not easy, and I encourage you to go to the paper and see how exactly we do it. But in addition, we keep for each process an array, a possibly infinite array, which has an entry for each of its operations. And in this entry, this array serves two purposes. First, the process says what fetch and add operation it's going to do, and then after it records itself in the vector, it is used to record its response value. Okay, so this is the high-level description of the algorithm. So consider this second process. It has done so far 4 fetch and add operations. So 4 entries in the array are filled. And then it wants to do its fifth operation. So it writes, this is the first step, it writes in its infinite array a new entry that has a sequence number, just 5, and then its total contribution, basically all the arguments it has in its sum of all the arguments it had so far in its fetch and add operation, including the new one. And then it goes and increments its vector timestamp in the shared vector and returns a vector of all the sequence numbers, and this will serve as the vector timestamp of its operation. Finally, it goes back to its infinite array, and in the same entry, 5, writes the vector of sequence numbers. It keeps the total contribution and writes the response that it should return for the fetch and add operation. And that's it. So we have these 3 steps: writing, announcing the operation we're going to do, persisting it in the shared vector array, and then writing the response and persisting it in your local array. Upon recovery, what we do is obtain from the memory the set of all operations. And basically, we look at them and we have 3 sets of operations. First, those that did A but never got to do B. These operations are invisible and did not take effect, and we just throw them out. Some operations manage to finish their C step and persist themselves in the infinite array, and these already have a response, and it's easy to recover them. So our main issue is the operations that persisted themselves into the vector, the big vector, but didn't persist their final response into their own array. Okay, so they did B but not C. And these are the effective operations, but not persistent. Okay, and the reason they are effective is because other processes will depend on them. Other operations will depend on their results, so we must take them into account when we reconstruct the operation upon failure. Okay, so we'll concentrate on these, and to explain how this is done exactly, I'm going to run the previous example on this execution. So run this execution example. So we have, again, the same 5 operations. I do the fetch and add, store 1 in the first entry, and then I actually record my sequence number in the vector. Then second process starts, records its contribution in the array, and then writes itself into the vector timestamp, and then fourth operation starts. The operation by the fourth process starts, writes in its infinite array its contribution. Then the second process completes and writes its final value in the infinite array. And then, here we see that this value reflects the contribution of the first fetch and add. And then second fetch and add by fourth process records itself in the infinite array, in the vector array. Operation by third process starts, records itself in the vector timestamp, and then fifth process starts, records itself in the vector timestamp, and then persists its response. And now, again, this reflects all previous contributions. And now, again, the system crashes. Now, upon recovery, what we do is basically we look at the memory. And if we have been careful enough, we can recover from the memory all the operations, the fact that we had all these 5 operations. Now, first thing we'll do is we'll discard invisible operations and assign a response value bottom for them. But note that in the example we didn't have invisible operations. All operations passed their B step, so to speak. Then we linearize the persisted operations. And in this execution, we have 2 persisted operations, the one that are shown here in dark gray. So it's this operation, and we linearize it basically using its vector timestamp, which is written here as part of this gray information. So I linearize this first operation, and then this is the second persisted operation. I linearize it. And now I come to the difficult part, and this is the effective but non-persisted operations. These are the ones that took effect in the vector timestamp, the big vector, but didn't manage to persist their response in gray. And note that we have at most 1 such operation for each process, because if I failed in the middle of an operation, I was in the middle of a single operation. So I go over these operations by order of process IDs. Okay, so I have at most 1 per process, so I go over them by process ID. So I go first for this one, this operation, and then from its vector timestamp, or basically from the vector timestamp of this operation, I realize that this operation has seen this the first fetch and add. So it must be linearized before it. Then I go and I need to look at these 2 operations. I go first for the fetch and add of 4. Although it started later, it is by a process by a smaller ID, so I consider it first. And then by looking at the timestamp of the brown operation here and the green operation here, I could detect that this operation must fit between these 2 operations. I will also see that this operation must fit between them, but actually I don't know in which order. Okay, but I'm going to order them arbitrarily. So I'll order this one first because I consider it first, and then I'll order this one second because I'm considering it later. Okay, and this is the final linearization for this operation. Of course, the actual proof and way we linearize is more complicated, and I urge you to take a look at the paper for the formal details. So far, I've assumed that processes fail and, importantly, recover together. In the paper, we also extend the algorithm to the model where processes crash and recover individually. But in the recovery, they wait for each other before they find a way to linearize themselves. Basically, they cooperate to execute a similar algorithm. And we also show in the paper that no algorithm can avoid this kind of waiting pattern. So if we have two processes, an implementation for two processes, an RL implementation of fetch and add from non-recoverable fetch and add reads and writes, it must have wait-free. It cannot have wait-free fetch and add and recover. The proof uses a fairly standard bivalence operation, similar to the proof showing that you cannot do consensus for three processes using fetch and add. But remember, we have only two processes. So the trick is that when we have failure and recovery, basically we can fail and recover a process in order to make it appear as if it's a third process. Again, the details are in the paper, where we also discuss weaker progress conditions under which the theorem holds. So this is mostly what I want to say. Let me finish with my last slide about future work. So obviously the space requirements of this algorithm are pretty bad, and it would be nice to find nicer, more compact representation. We have some suspicions that the big vector timestamp cannot be avoided, but I'll be happy to be proven wrong. Also, for if we want to use this implementation in other contexts, it would be nice to have fewer RMRs, remote memory references, in the algorithm. Clearly, the algorithm is not very practical. It would be nice to make it more practical. And finally, it would be nice to have self-implementations of other primitives. My own favorite is swap, because swap is in some sense sort of universal for level 2 of the consensus hierarchy. So with that, let me thank you for all listening from abroad, and I'm happy to take questions.
The next talk is Strongly Linearizable Linked List and Queue by Hwang, University of Waterloo.
Hello. Yeah, this work is on strongly linearizable linked list and queue. Apologies for being late. I'm Hwang. I'm from the University of Waterloo, and this is joint work with my former supervisor, Philipp Woelfel. So I will first introduce and motivate strong linearizability as a correctness condition. So in the shared memory model, asynchronous shared memory model, linearizability is considered the gold standard of correctness conditions for distributed algorithm designers. And it's when operations appear to take effect at a point in time. And due to this notion of taking effect at a point in time, it was thought to be practically equivalent to atomicity. But in one way in which linearizability is weaker than atomicity is when using randomness. And Golub, Heim, and Woelfel showed that a strong adaptive adversary has more power with randomized algorithms using linearizable implementations as opposed to atomic objects. In particular, they showed that a strong adaptive adversary can skew the probability distribution over the set of outcomes when using linearizable implementations over atomic objects. And they proposed strong linearizability to address these inadequacies. They showed that it preserves the same probability distribution as atomic objects, and they also showed that it was a necessary and sufficient condition to achieve this. So intuitively, an implementation is strongly linearizable if it's linearizable, and it imposes one further condition where future execution does not affect the linearization points of past operations. In other words, the linearization order should not change retroactively. And this diagram shows something that should not happen for a strongly linearizable implementation, where you have a past represented by S, and some future event after S affects the linearization order of operations in S. One good property of linearizability that it's composable. So this means that if you have a linearizable implementation with atomic objects and you replace those atomic objects with linearizable ones, the overall object is still linearizable. So it's very good for modular programming. You can assume things are atomic, build linearizable implementations, and replace them with linearizable implementations of their own. Strong linearizability is also composable. And due to its newfound nature, not many strongly linearizable implementations are currently known. And in particular, almost nothing about strongly linearizable implementations are known when using practical strong primitives. And to close this gap, we look at two well-known caste-based lock-free data structures, and we show that they are not strongly linearizable. And what we take a look at is Harris's linked list and Michael and Scott's queue. And we also derive modifications to make them strongly linearizable. Next, we'll go over Harris's linked list. So Harris's linked list has the following fields. It has a key value, which is the element that the node contains, which it has a successor field, which is a composite field composed of next, which is the next node in the linked list, and marked, which is a Boolean value to indicate the marked status of the node. And the key idea behind Harris's implementation is that nodes are marked for deletion before actually being removed from the list. And it also maintains invariance that the elements in the linked list are sorted and unique, and the key does not change after initialization. And they maintain head and tail sentinel nodes with keys negative infinity and infinity. So Harris's linked list supports 3 operations, and every operation returns a Boolean value to indicate success or failure. So an insert should succeed when the key being inserted is not in the linked list and fail otherwise. Likewise, delete should succeed when the key is not in the linked list, and find returns whether a key is in the linked list. So Harris's linked list works by using the search helper function, takes key as an input and returns two nodes left and right with the following guarantee. At some point in time during the execution of search, the left key should be less than the search key, which is less than or equal to the right key. Right should be adjacent to left, and left and right are not marked. And the intuition behind this is that if the right key returned has the same key as the search key, then the search key was in the linked list when the search conditions were true. And if the right key is less than the search key is less than the right key, then the search key is not in the linked list when the linked list is when the search conditions were true. And these are when find operations and failed inserts and deletes should linearize, because they only have to confirm or deny whether a key is in the linked list at some point in time. And yes, this is what we see happens. For example, in the find method, the nodes left and right are returned, and then right is checked if it contains a search key, and so on. Same for the delete method. A failed delete method linearizes when the search conditions were true. So one possible indication of an implementation not being strongly linearizable is when there's a response where the response isn't determined. There's an operation where the response isn't determined at an operation's linearization point. If this is possible, then we could have an execution where we schedule a future event after the linearization point to change as a response. And likely the linearization order of past operations will likely have to change to accommodate for this change in response. So this is, in particular, this is true for Harris's linked list. So by using this observation, we'll construct a counterexample for the implementation being strongly linearizable. And we consider the following past execution and two different extensions to that execution. So if we trace the past, well, P first successfully inserts 3, and delete executes up to line 15. That is right before the red highlighted section. So one thing to note is that when Q proceeds with its execution, it will check whether the right node assigned is marked or not. If it's marked, then the search will search again, restart, or it will return the current left and right nodes. And currently, head is assigned to left, and the node containing 3 is assigned to right. If we fully trace the execution, then P also successfully inserts 2. Looking at the first extension, when Q resumes the execution, it will see that in the search, the right is unmarked, and it will return the left and right nodes. And because the return key 3 is not equal to 2, the delete method will fail. And remember that all the inserts have succeeded. Now considering the second extension in the same scenario, but however, this time there's a delete of 3 scheduled by P. So the node containing 3 is marked. And when Q resumes as execution, it will see that it is marked and restart. And eventually, when it restarts, head will be assigned to left, and the node containing 2 will be assigned to right. And Q will successfully delete the node containing 2. In particular, every operation in this execution has succeeded. So we see on the left the 2 executions that we considered, and on the right, their linearizations. One thing to note is that the delete of 2 must be scheduled before the insert of 2 in the first extension, because the delete of 2 fails. And in the second extension, in the second linearization, the delete of 2 is ordered after the insert of 2, because the delete of 2 succeeds. So the linearization order of the past has changed, and this linked list is not strongly linearizable. One thing to note is that for successful inserts and deletes, for successful inserts, the operation linearizes when a node is successfully inserted by a successful cast operation. And also for delete, the operation linearizes when a node is successfully marked for deletion. And these are both strong linearization points because they correspond to a successful cast operation. After a cast succeeds, no feature event can influence whether that cast operation succeeded or not. So this sort of foreshadows our modifications, which focuses on the search method. And our new search method will guarantee a different set of conditions. Now, at the last shared memory step of search, the left key will be less than or equal to the search key, which is less than the right key. Right will still be adjacent to left, and left will be unmarked. Now recall that with the old search condition, I guarantee that the following, the difference being now the left key may contain the search key, and we no longer need right node to be unmarked. And the idea is true as, the same idea is true as well, where these operations will linearize when the search conditions were true. In this case, which will be at the last shared memory step of search. So our search method guarantees this in the following way. It maintains 2 pointers of nodes, cur and cur next, and these are potential candidates to be returned as the left and right nodes. So cur is originally initialized to head, and cur next, the next of head. And next, it evaluates the key conditions of our search condition, whether the cur key is less than or equal to the search key, which is less than the cur next dot key, and in the orange box. And if this is false, then we're at the wrong location of the linked list, and we set cur to cur next to iterate further down the linked list. If this condition is true, then we next determine whether the current node is marked. If it's not marked, then we return the cur and cur next as the left and right nodes. Otherwise, if it was marked, then we excise the current node, and we set current to head, and then restart the traversal. And we have to restart the traversal because we may be traversing a set of nodes that have already been excised from the linked list. And from this flowchart diagram, it's clear that the conditions were true the last time current.successor was read. This is when every variable that was used in this exit condition was known. And by the same reasoning, it is determined at the last shared memory step what nodes were returned. So after the last shared memory operation, which is the read of current.successor, no future event can change what the search returns. And thus the operations are now strongly linearizable using the search method. So other methods are largely identical. The difference being that now the left key is checked whether it contains the search key. The largest difference can be seen in the delete method, where we no longer attempt to excise a node that was marked right after we mark it. And now we will look at Michael and Scott's queue. So the queue is a linked list based queue, and it maintains a dummy node, which simplifies its cases for empty nodes. And the head and tail are originally initialized as a dummy node. An in-queue operation appends a node at the tail, and it changes the tail to the recently appended node. And a dequeue operation moves head down the linked list, and so the head points to the last node that was actually dequeued. And notice that the linked list is empty when the head points to the last node in the linked list. And it maintains this property where the head is never behind, or rather the tail is never behind the head. And as expected, an in-queue linearizes when a node is successfully appended to tail. And this is done by a successful cast operation. And again, this point is strongly linearizable. And for dequeue, a successful dequeue linearizes when the head is successfully iterated down the linked list. And again, this is done by a cast operation and is therefore strongly linearizable. And unfortunately, this implementation isn't strongly linearizable because of failed dequeue operations, and they linearize when a null value is read from headness. So when it verifies that the head is the last node in the linked list. And it's because right after reading the head.next, what it does is it checks whether the current head value that was read is the same as the head value, whether the head value that was read is equal to the current head value. And so if the head was changed between when the next was read and when this if condition is evaluated, then the dequeue will restart. And again, the response is not determined by its linearization point. And we can, again, construct a counterexample to the implementation being strongly linearizable. And so we had this pesky if condition that prevented strong linearizability. Actually, the interesting fact is that if we simply remove this if condition, then the implementation becomes strongly linearizable. One thing we have to note is that we have to check whether this condition is always true when null is read from start.next. And it's always true because of the property that I mentioned about the implementation where the tail is never behind head. So if which means that if the head points to the last node in the linked list, the tail will also always point to the last node in the linked list. And thus this if condition will always be satisfied. And now the response is determined at the linearization point. And we can show that the resulting queue is strongly linearizable. So to conclude, I'll mention some future works. So we have this vast library of linearizable implementations, but not so much with strongly linearizable ones. So the natural course would be to come up with more strongly linearizable data structures, or especially synchronization primitives, because strong linearizability is a local property or composable property. That would be very useful to develop further implementations. And the development of techniques to prove or disprove whether linearizable implementations are strongly linearizable. So we've often used this possible indication that if a response is not determined at its linearization point, then we can often construct the counterexample to the implementation not being strongly linearizable. But does this observation directly imply that an implementation is not strongly linearizable? And also, it'd be nice to have techniques to develop strongly linearizable data structures in general. Thank you. That was my talk. I'll take any questions.
Thank you for your next Any question? No. So I have a small question. You did a small change to prove a stronger consistency. Do you know if these small changes affect the performance of original data structures?
I believe that for Michael and Scott Q, I don't think. Well, I haven't formally analyzed, haven't done any particular amortized complexity or experimental evidence, but I would guess that for Michael and Scott's Q, the performance, it was just a removal of an if condition and therefore wouldn't be as bad. But I think for Harris's linked list, the performance of the new data structure would be at most as best as in the best case, it will be as good as Harris's implementation. One problem is that because the delete no longer tries to excise the node that was marked, you could have and actually the new delete condition only marks a node. It doesn't try to physically remove it. It leaves a search condition to do that. So you could have a condition where you insert like 3 nodes, 1, 2, 3, you mark it, and then none of the other linked lists ever touch those nodes. And it's in the linked list, but it's marked. But now every operation afterwards has to traverse those 3 nodes to complete its operation.
Okay, thanks. Any other question? No, so thanks again, the speaker.
Thank you.
So the next talk is using nesting to push the limits of transactional data structure libraries, and the speaker is Gal Assa.
Thank you. So hi, my name is Gal. I'm from the Technion in Haifa as well. This is joint work with Hagar, Guy, Idit, and
closer to the mic.
Okay, it's okay. Okay. And I will talk today about using nesting to push the limits of transactional data structure libraries. So I will start by getting you into the context of what transactional data structure libraries are, and then I'll tell you a bit about how we added support for nesting, and what we discovered about why we should use nesting when we use transactions and transactional libraries specifically. Afterwards, I'll tell you about how we expanded the library with some more data structures, and I'll finish with a new benchmark and some evaluation results that we received. So let us start with the context. So transactional data structure libraries were used to applications using data structures to manipulate data and the structures. So the TDSL concept was to wrap these data structures in a transactional library and provides some software transactional memory programmability, meaning you can have a transaction, so you hide the concurrency control from the user, and you may have as many operations as you want within the transaction. The thing about TDSL that differs it from regular STMs is that the data structures are custom tailored to be highly concurrent and effective. The drawback, however, is that it's not as general as software transactional memory, which allows you to have transactions on basically everything. A basic comparison would say that TDSL allows us to decide how to do the concurrency control with respect to the data structure in use. So we can be pessimistic on certain data structures like queues and pessimistic on others. And the conflict detection as opposed to STM is done based on a semantic level, meaning if we iterate over an entire list, we don't need to put every element in our read sets because it doesn't matter. So we have smaller read sets and thus less aborts. But we need to remember that only data structure accesses are safe. This is kind of similar to concurrent data structures and unlike, again, STM. I'll continue with a short reminder of how transactional memory would generally work. So at the beginning of a transaction, we initialize the local read set and the local write set that represent what we read and write respectively. And we have a toy transaction over here for the example. So let's say the first thing we wanted to do is say B equals A. So we take B and put it in our local write set and A in our local read set. Then we do some manipulation to B's value. And finally, we say that C equals A plus B. And what we need to notice here is that C does not read B from, the third line does not read B from shared memory, but from the write set, because eventually we want this code to be equivalent to some sequential execution. And when the transaction ends, if everything is okay, we try to lock B and C and validate A to see that no one changed it, so the transaction can still serialize. And if everything is okay, we reflect B and C to shared memory. So this would be like a very basic transactional memory algorithm for us. The problem with transactional memory is basically a scalability issue. We don't see a lot of use of STM because when there's a lot of contention or when transactions become longer, transactions tend to abort a lot, and when they abort, they waste a lot of work, and then we feel it in the performance. And what we try to understand is if we can save some of this wasted work and perhaps do something better with the time. So this is where nesting came to our rescue in a sense. So I'll tell you a bit about how it works in TDSL. So let's say the external transaction, we sometimes call it a parent. It has its code, and we define some section of it as a child transaction or the nested part. And the parent transaction, the parent's code, just executes sequentially. And when that aborts, the entire transaction aborts. When it commits, of course, the changes are reflected to the shared memory. But within the nested part, we do something else upon abort. If the nested part aborts, we ask whether we can retry only the child transaction and not everything we did before. And therefore, we can save things that happened prior to the child transaction. And when the child commits, it does not update the shared state, but only the parent's local state. We migrate what we did over there. So this is the basic scheme. I'll exemplify using a queue. So we have another toy transaction on the top right of the screen. It does a lot of the queues and then a queue again. So in order to not change the shared queue when we queue items, we have a pointer that moves because we don't want to get items out before commit, but we can read the values. So upon the first dequeue, we return the value and move the pointer. And again for the second dequeue, and then we have consumed the entire shared queue. And then we go on to consume the parent's local queue. Again, upon dequeuing, we cannot remove items yet because the child transaction didn't commit. So we only move the pointer, but when a child performs a dequeue and eventually wants to dequeue an item of its own, there's no problem to actually remove it. And if we want to enqueue to the child, it's pretty simple. We just enqueue an item to the back of our local queue. So this is how we did it with the queue. And we had implemented similar things with TDSL's skip list as well. And after doing that, we started asking, okay, is it good? When is it good? When can we use that? So we conducted a short micro benchmark with operations on the skip list and the queue, and wanted to understand when the scheme is useful. So what you can see here are the throughputs of some of our experiments. The x-axis is the number of threads, and the y-axis is throughput. And you can see that when there's not a lot of contention, like when the number of keys on the skip list is large, nesting the queue operations actually helps a lot. And nesting the list operations doesn't have a lot of impact. But still, it really helps compared to not nesting at all. However, when there's high contention and the key range is small, nesting doesn't really help, and in fact, we lose most of the time because we just have more overhead. We wanted to see how this looks in terms of abort rate. So this is the abort rate with respect to the previous slide, and we see that for low contention, around 8 threads, almost all the transactions without nesting abort, which is not very good, but with nesting we can reduce that by about half. However, with high contention, it doesn't really help. Nesting could not help when there was contention. So we had a slightly bit less abort rate, but it generally created more overhead and did not translate into better throughput, as you saw before. So then we try to characterize when nesting is more helpful, and essentially our first understanding was if the operation that caused the abort of the nested transaction is likely to succeed if tried again, it's worth nesting. But this is only true when the work we save is worth the overhead that we induced. And if there's high contention, nesting is not magic. You can't hide contention by doing something within the transaction. So these were our first understandings. Next, we added some new data structures to the library, which, as I said before, contained only a queue and a skip list. We added a stack, a log, and a producer-consumer pool. All supports both transactions and nesting within transactions, and these are the APIs. The log has a read and append, and the producer-consumer pool, of course, has produce and consume. And I will talk a bit more about the stack, where we had a nice understanding while implementing it. So let's say that a transaction pops items from the stack, and it has previously had 2 items in its local stack. So when we pop, we just take an item out of our local stack, and we don't need to modify the shared state. So we can just keep on and doing that without locking the shared stack. However, when we do want to pop something from the shared stack, we should actually lock it, because if our transactions succeed, other transactions won't. So we lock it, and this is how we signal other transactions you're going to abort. And so you should retry now. But until that, whenever you have more pushed items than popped ones, we don't need to interfere with the shared stack, and more transactions can actually commit concurrently. The final thing I'm going to present is a new benchmark that we conducted, and some evaluation highlights. So our benchmark is based on network intrusion detection system, kind of like Intruder. We took one of the designs from the original paper and rewrote it in Java. So we have producers modeling input from the network, capturing packets and putting them in a packet pool, and then consumers that do all the data processing and report good or bad packets to some shared output entity, say a log. So this is our benchmark. It's pretty configurable. You can control the number of packets and how many bad packets are of each type. So there's a Java implementation for that. And we wanted to test it against some more soft and transactional memories. And the results are here. So I'll start from the top. When we nested both map, there's a map that maps fragments to full packets. When we nested maps and logs, where the output is log operations, we experienced a big boost in performance. And as you see, the performance scales with the number of threads up to about 40, which was pretty nice for us. However, when we only nested the map operations, which happened somewhere in the middle of the transactions, we did not find much benefit compared to not nesting at all. And when we did that compared to other SDNs, both with regular and elastic transactions, so the performance was about half as good as flat TDSL. So this was our performance highlights. And that would be it. So to conclude, we found out that nesting allows longer transactions to commit and waste less work, so we can have better performance. We have a new benchmark for testing Java transactional frameworks, and we have both library and benchmark open source, so feel free to use them. And that would be it.
So the last talk is non-blocking dynamic unbounded graphs with worst case amortized bounds, and the speaker is Muktikanta.
Yeah,
Sorry for
thank you.
misspelling.
Nice. Good afternoon all. Thank you. So hello. So I'm Muktikanta. This is joint work with Bapi Chatterjee. Earlier he was in the IST Austria. Now he got a position at the IIIT Delhi. And my previous supervisor Sathya Peri and one student Manogna and myself. This talk is about non-blocking dynamic unbounded graphs with worst case amortized bounds. So let me give some motivation of why need for the non-blocking dynamic graph. So as you can see, this is a graph, a social networking graph, right? So each users are connected with the other users, some social information. So I can represent each user as a vertex of a graph, and the relationship between other user I can represent as an edge. Generally, these graphs are dynamic in nature. Dynamic, I mean, some users can come and go, some edges also can come and go. So on that graph, I want to perform some query operations. Query operations, I mean, so whether Bob is reachable from the Brown. I mean whether there is a path from Brown to Bob. Similarly, I want to find what is the shortest path from the Alice to Bob. Okay. Similarly, I want to find who is the most influential person in the graph. I mean influential means the number of shortest paths passes through a vertex. Like in this case is seed. So if graph is not dynamic, I mean static, so to answer these queries are very simple and straightforward because efficient algorithm is already available in the literature, right? So for the reachability case, I can apply breadth first search or depth first search, and my query can get very fast. Similarly, for the shortest path case, I can apply the digestion algorithm. If edge weights are negative, that case I can apply the Bell-Manford algorithm. My job done. Similarly, for the influential case, I can apply the Brandt's algorithm to find the between edge centrality, and my job is done. Now the problem arises if the graph is dynamic, and they design that graph in non-blocking way. So to ensure, if graph is dynamic, to ensure these queries are very hard. So at first, what we try to design, at first we design a non-blocking graph, which is going to support the dynamic updates. Dynamic means insertion, deletion of vertices, and insertion, deletion of edges. On top of that, we try to ensure this query in non-blocking way. So that is our motivation. So based on these motivations, we try to ensure these edit operations. So first, add vertex. We're going to add a new vertex to the graph, if not present earlier. Similar to remove vertex, is going to remove an existing vertex from the graph. Contents vertex is going to find a vertex is present or not. Add is going to add a new edge to the graph. Remove edge is going to remove it edge from the graph. And context edge is going to find check whether edge is present or not. And these are the three query operations we targeted. So breadth first search, single source shortest path, and between centrality. So based upon these edit operations, at first we want to design a data structure which is going to support dynamic operations. So this is the data structure we first designed. Means earlier we proposed some inefficient one. We derived to a efficient one, this one. So you can see at first we targeted for the directed graph. So you can see this is a directed graph. The graph is represented, its composition of log-free hash table and dynamic binary search trees. Binary search tree which both are log-free. So you can see 4 vertices, 5 vertices, they are mapped to a hash table which is non-blocking and that is dynamically resizable. So you can see the vertex 1 and 5 is mapped to the bucket 1, which as usual hash mapping function x mod 5. And each adjacent nodes of a vertex are represented as a log-free binary search tree. Node 5 adjacent search 1, 7, and 4, they are represented in a log-free binary search tree, you can see. And very interesting, we add some optimization here. You can see there is a shortcut pointer from each edge node to corresponding vertices. So why you need it? So while performing any query operation or exploring all the edges of a vertex, so while exploring, let's see 5 vertex I'm there, I want to explore all the adjacency vertices. Means 1, 4, 7. They are the edge nodes. The edge concurrent updates are going on. The vertices, the edge is present here. The corresponding vertices might be deleted by some other threads. So we need to verify whether that edge is valid or not. So if I have these shortcut pointers, through these shortcut pointers I can check whether the corresponding vertex is valid or not. Although it is deleted from the data structure, but it is sitting idle in the memory. So we are not doing any garbage collection. That vertex, deleted vertex are sitting idle in the memory. So using these shortcut pointers, I just go and check it whether the vertex is valid or not. If these shortcut pointers are not there, I need to explicitly search and test whether that vertex is present or not, to test each edges are valid or not. So these shortcut pointers helps some better optimization. So this is the data structure we designed. So and combining this data structure and the framework we propose. So it is 3 query operations: breadth first search, single source shortest path, between centrality, and we consider here the only update operations. We skip the contents vertex and contents edge. And we prove all the operations are non-blocking with linearizability property. And we prove that our algorithm takes a very less memory pool. The whole we call it panigram. This word is taken from the Sanskrit in India. That means it's marriage between 2 persons. Okay, the marriage is nothing but to create a new relationship, and it's represented as a graph. So how you do framework we design? Each query operation generally we tackle, they have some starting source vertex. So op item nothing but the operation query, they're going to start from starting vertex B. So at first we'll check whether the vertex is marked or not present. If not present, I don't want to do anything, suddenly return. If that node is present and valid, I'm going to read the thread ID, the thread which is performing that query. Then I'm going to invoke the scan method. Scan method is performing very important role here. So how this scan method works here? At first it try to collect the query. Means starting from source, try to reach the nodes. Means that is just a partial snapshot. So because we are not scanning whole the graph, we are scanning the nodes which are reachable from the source node. So it store in the old tree, then it start collecting for the second time. So try to collect the tree again, and after collecting the 2 consecutive collects, it compare both the trees are equal or not. So if both the trees are equal, then it suddenly returns true, because during 2 collects, no updates happen within that time frame. So I'm getting a valid snapshot. So on that snapshot, I can perform any query what I am to do. So if that 2 consecutive collects are not equal, so what I'll do, I need to discard the old tree, copy the new tree to old tree, then start collecting again. This process I'm going to continue until 2 consecutive queries are equal, so that I will get a valid snapshot. On top of that, I need to do the any query operations. So based on how I'm giving this a theoretical means just explanation. So main tricky part is that any edge modifications happening, there is an atomic counter associated with each vertex. So that is going to increment it. Okay. So in the 3 collect method, going to return the BST minus search tree of the, so breadth first search tree of the what? All the vertices nodes, and the compare tree going to compare 2 trees along with the vertex counter present with the vertex nodes. If they are equal, then I'm going to return the tree valid snapshot. Otherwise, you're going to continue by discarding the old tree, and this process is going to continue until it is 2 consecutive scans are equal. Sorry. So then we try to prove all the edit operations are linearizable, and the query is individual the obstruction free. Okay, and the algorithms all are the log free. A proof are available in the paper. So let's go to the what my experimental results, because we have a lot of experiments performed. So we performed this 56 logical core machine, implemented C++ without garbage collection. We load the armature graph as well as real world graphs, and then after skipping some warm-up operations, we perform 10K operations. So with these distributions, so we took the query operation very expensive. So we took the 2%, the rest add vertex, remove vertex, add edge, remove edge. These are the distributions took it, and we could try to compare the things. These are the state of ours to try to compare it. So PGCN is the proposed one using double collect things, and we try to take the PGICN, which is inconsistent version of the panigram. In that case, we take only single scan, not double scan. And the Ligra and Stringer are the very popular graph analytics. So Ligra generally, they don't support the what dynamic operations like what we are proposing, because we don't find any graph analytics. We support all the update operations. So Ligra is a static graph analytics. So that supports only BAPS, SSP, and BC. Stringer, this supports what? Remove vertex, add edge, and remove edge, but it doesn't support the add vertices. First they allocate the number of vertices. Based upon that, they perform the operations. To make a fair comparison, what you did, so we try to implement the missing operations for Ligra and Stringer. So that case, to implement the add vertex for the what Ligra and Stringer, we did the what memory copy from the old graph to the new graph and try to add one vertex and release the old memory. That way, we did the memory copy of the old graph to new graph, and they perform the operations based upon these distributions. This is the one result for the BFS. Yeah, B is 1.3K, 1K which vertices and 2.4 million edges. After discarding the warm-up operation, we performed what 10K operations. And all these are the with these distributions, we see our is better. And sorry, yeah, we perform our cases PGCN. PGICN always be better because it takes only single scan. So PGCN is better as compared to Ligra and Stringer. Stringer doesn't scale anymore because it's taking the memory copy from the old to new. It's taking too much time, so it doesn't scale. So here is the more I try to do a lot of experiment for the increase the distribution of what BFS. BFS 60%, 40%, 30%, 20%, and see how it performs. Means we want to compare where we can able to beat the Ligra or Ligra just beats us. Sorry. So what we see, PGCN is perform better for the 56 threads or other things. So Ligra is that way. We are able to beat the Ligra because yeah, Stringer is we are not shown here because it's not performing at all. So we didn't see any results of Stringer, but Ligra able to beat it. So here the results for the SSP. SSP's case, Ligra is able to beat us in some cases if number of SSP is large. Okay, but we are able to beat the Ligra if number of updates are high. So all the cases Ligra perform better than us, but this case if updates are high for the 56 threads we are able to beat the Ligra. So here the results for the between decentrality. In all cases we are able to beat the Ligra, and more results here for the BC. In all cases we are able to beat the Ligra also. So we try to compare another graph analysis called Graph1 is famous, but that Graph1 only provide the add edge and remove edge. And so we are unable to crack how to do the add vertex and remove vertices because the course is very complicated. We try to talk with the author, they not responded properly. So we try to fix the number of vertices and try to perform. Still we are able to beat the Graph1 also. So they are the memory footprint. Okay. We compare the memory footprint for all the cases for particular distributions. So for the BFS case, yeah, Stringer is taking too much time, too much memory. It's around 1000 MB, more than 1 GB, and for our case, it's taking 200 MB is enough for us. And Ligra is taking around 1 GB data. For the SSP case and BC case, so our node is become very fatty, so it's taking more size as compared to Ligra. So PGCN is taking the more memory. So these are the average number of scans algorithm going to terminate if I'm taking the PGCN. Okay, for the BFS case, it is going to average number of scans is 2 or 3, around 2 and 3 is enough for us to terminate the algorithm. For the SSP, 3 is enough, and for the between the central is 2 scans are enough to terminate the algorithm. Yeah, that's all, and come to my conclusion. So we implement the concurrent graph, which is the composition of log-free hash table and binary search trees. So we compare all the 3 query operations we implemented. We compare the result with Ligra, Stringer, and Graph1. I implement the C++ without garbage collection. We experiment with certain micro benchmarks. So what I found, all cases our performance better, but in some cases Ligra performs better if graph size is larger. So Ligra is taking the advantages of the parallelism. So in that case Ligra is performing the better in some cases. Yeah, that's all. The more report, the technical report is everywhere. GitHub, in the GitHub you can find the code, you can plug and pick anything. That's all. Thank you. I'm ready for take the question.